Hello, this is finding both the empirical and molecular formulas. We have dibutylsuccinate at 62.58% carbon, 9.63% hydrogen, and 27.79% oxygen, and the molecular mass is 230 atomic mass units. I want us to visualize this first. We have a molecule called dibutylsuccinate. We know the percent composition. We know there's 3 atoms, carbon, hydrogen, and oxygen, and we know its molecular mass. So section A, we need to find the empirical formula, and section B, we need to find the molecular formula. The empirical formula is the simplest formula that can be, whose subscripts can be written in the lowest terms possible. Well, it's sort of like reducing, like if you have a fraction 15 over 10, you could reduce that to 3 over 2, and that's like the best I could explain that right now. So the step 1 in section A of finding the empirical formula is to assume that you have 100 grams of this molecule, dibutylsuccinate. If you assume that you have 100 grams, well, 62.58% of it will be carbon, 9.63% will be hydrogen, and 27.79% will be oxygen. Okay, so if you assume 100 grams, let's write that down. You have 62.58% being carbon, 9.63% being hydrogen, and 27.79% being oxygen. So if you have 100 grams, 62.58% of it will be 62.58 grams of carbon per 100 grams of the molecule. Likewise, you'll have 9.63 grams of hydrogen for every 100 grams of the molecule, and you'll have 27.79 grams of oxygen per 100 grams of the molecule. It's very intuitive. Just to check, you could check, make sure that it adds to 100 grams, because as you know, matter is neither created nor destroyed. You can't have more than 100 or less than 100. So now we need to convert grams into moles, because in a formula like H2O, the ratio is 2 moles of hydrogen per 1 mole of oxygen. So let's start with carbon. Okay, we need to convert grams to moles, so I'm going to assume that it's easy for you by now. You have 62.58 grams of carbon, and there's 12.0107, there's a decimal point there, grams of carbon per mole of carbon. So we're using dimensional analysis. The grams of carbon cancel out, and that's going to approximate to 62.58 divided by 12.0107 is about 5.210 significant figures, because there's 4 here and it's a division problem. 35 moles of carbon. Next, go to hydrogen. You have 9.63 grams of hydrogen times 1.00794 grams of hydrogen per mole of hydrogen, and as you use this a lot, it's going to be very fast and easy for you to memorize a lot of these, a lot of the masses of the average, weighted average of the elements, like 1.00794 for example. So this is what I got on the calculator, and significant figures because there's 3 here. Moles of hydrogen. Well, I forgot today was garbage day. Anyway, oxygen, 27.79 grams of oxygen, and there's 15.9994 grams of oxygen per mole of oxygen. Let's go to the calculator. 27.79 divided by is about 1.73 36 vertical dash line 94 moles of oxygen. Now notice that that is currently the smallest one when it comes to moles, but it's not the smallest in weight. That's why you have to convert to moles before you write down your tentative formula. So since I said before, like H2O, that means there's 2 moles of hydrogen per every 1 mole of oxygen. Basically now you could write down a tentative formula using what you got here. So you got C 5.210. I'm just going to round now using the significant figures. And here is your tentative formula. Imagine how nightmarish it would be for every formula that we know be something like this with decimals, so we need to get rid of that. But first, we're not done yet. We have to take the smallest amount, which is oxygen, and we have to divide each of these by the smallest amount, which is 1.731. And when we do that, the oxygen is going to go to 1. So, and then we could work from there. So this should equal C, so 5.210 divided by 1.737. Oops, that's got that right? Yep. So it's about 2.999. Okay, and then H 9.55 divided by 1.737 is about 5.498. Then we have O to the first. Now let's round this to even numbers. Now here's what we need to consider. This is so close to 3, so we'll round it up to 3. But don't round this down to 5 or up to 6 for some reason. But don't round when it's so close to like 0.25 or 0.5. Don't round it all the way down. We want to round it to 5.50 because if you round it all the way down, you're taking a part of the mass away, and of course mass can never be destroyed. And if you round it up for some reason, if it's like 5.698 for example, you can't round up because you're adding mass, and you just can't do that. It's best to just go to like 0.25 or 0.5 or maybe even 0.75 and work with that. And then we have O. So now we have a decimal place again, or I mean decimal point, 5.5 here. Again, so we gotta get rid of that decimal, so we just multiply the subscripts by 2, which should be C6, and it's just like algebra. So this is the empirical formula. So that is in fact the empirical formula right here. But is it the molecular formula? Well, we first need to find the molar mass of this empirical formula, and to do that, I'm just going to use round numbers here. You got, I'll just do it. I actually like these problems. 0.0794. So what I done is I took 6 moles of carbon, which is approximately 12 grams per mole, 11 moles of hydrogen, which is approximately 1 gram per mole, and 2 moles of oxygen, which is about 16 grams per mole. More precisely, and to save time on talking, is that this, the molar mass of C6H11O2 is approximately 115.13 or 1395 or 140, that's a 4, just rounding, and that should be atomic mass units, we'll call it. So that's how you get that. Now, is this the right formula? Well, you go to the original molecular mass. So again, you have diabedosuccinate, you know the percent composition of each of the 3 atoms involved, carbon, hydrogen, and oxygen, and you were able to weigh out the molecular mass of being 230 U. Here this empirical formula is 115 U. So to determine the molar mass, you have to take the original molecular mass, which is 230 U, and divide it by the mass of the empirical formula, which is 115 U approximately, which, guess what, happens to be 2. So, what that means is that this empirical formula is essentially half of what it's supposed to. It weighs half. This is in fact the same percent composition, but it's half of what you need. So the real formula is C. So remember, you multiply each subscript by 2, so that's really C 6 times 2, H 11 times 2, O 2 times 2, which is about C12, H22, O4, and that is how you determine the molecular formula by first determining the empirical formula. Also, real quick, you could, just like in algebra, you could go back and check. You could take this and figure out the percent composition just from the formula. So like you have 12 moles of carbon and there's 12.0107 grams per mole, and you could essentially find out the mass percent of each of these atoms, and I might do another video later on. Thank you, everybody. I'm not going to ask you to like or subscribe. I'm passionately doing these videos from my heart. I'm not calling any of my videos perfect or ideal, relatively speaking. Besides, this is merely a fraction of a 1/4% of all the myriad of videos out there concerning this subject, including videos with more easy to understand animation and explanation. Nevertheless, I am intending to make as many videos as I can, just to be a help out there. But I'm simply one voice out of many. Thank you.